Excellent, thank you.
The broadcast is now starting. All attendees are in listen-only mode.
Good day, everyone, and welcome to the DOE Fuel Cell Technologies Office monthly webinar series. In today's installment, Max Way of Lawrence Berkeley National Lab will discuss their work in total cost of ownership modeling for stationary fuel cell systems. My name is Chris Worth, and I'm the organizer for this meeting. We'll begin shortly, but first I have a few housekeeping items to tell you about. Today's webinar is being recorded, and the recording, along with the slides, will be posted to our EERE website in about 10 days. We will send out an email to attendees once those are posted to the site. Next slide, please, Max. All attendees will be on mute throughout the webinar, so please submit your questions via the question box that you should see in your webinar panel. We will cover those questions during the Q&A at the end of the presentation. Next slide, please, Max. With that, I would like to introduce our DOE host, Donna Ho, joining us from the Department of Energy headquarters in Washington, D.C. Donna is a technology manager within the Fuel Cell Technologies office. It's a pleasure to have you, Donna. Good afternoon.
Good afternoon. Thanks, Chris. Welcome to everyone. I'd like to introduce our speaker for today. This is Max Way, who is a program manager in the Sustainable Energy Systems Group at Lawrence Berkeley National Lab. He has 11 years of industry experience in the semiconductor industry and has worked at Lawrence Berkeley for the past 7 years with a focus on multi-sector modeling and techno-economic analysis of various technologies, including fuel cells, cooling equipment with low GWP refrigerants, and electric heat pumps for building heating. He is currently leading a deep decarbonization study for California and a cost study for net zero energy homes. Welcome, Max.
Thank you, Donna, and thank you, Chris, and thank you everyone for joining. It's morning out here in California. So I just wanted to start with thanking my research partners. So I'd like to acknowledge and thank the partners at UC Berkeley, two groups, one in the Laboratory for Manufacturing and Sustainability, Department of Mechanical Engineering, and just want to dedicate this in memory of Professor David Dornfeld there, who just passed away. He was the chairman of the department there. And then also I'd like to acknowledge my co-PI, Tim Littman, who is the co-chair of the Transportation Sustainability Research Center, also at UC Berkeley. Also would like to acknowledge and thank working partners at Strategic Analysis, Brian James and Whitney Colella, for their help in system designs and functional specs. Also, I'd like to acknowledge and thank Ballard Power Systems for their partnership in developing the PEM cost analysis. So shout out to Paul Beatty and Patricia Chong. We've had a lot of other collaborators which are at the vendor level, but no other funded subcontracts, and in particular we consulted with Altergy for backup power systems. So, okay, so the outline of my talk is as follows. I'll be describing our modeling approach, overall modeling approach for total cost, and then I'll be going more into detail into several topics into direct cost modeling, where direct costs are estimated for various system sizes and various manufacturing volumes. And then I'll describe some cost comparisons to existing systems. It's important to try to have some comparison to either existing price data or the cost studies. So there's available data from Japan for micro CHP, some more limited data for backup power systems. And then finally, I'd like to spend some time on the externality valuation piece, which is really looking at the benefits of something like a fuel cell system, which is providing cleaner power in terms of human health impacts, so cleaner air and environmental impacts. Those impacts are dominated by human health, so that's really the focus there. And I'll provide a valuation example, sort of the societal valuation for fuel cell CHP and small hotels, and then I'll conclude the talk. Okay, so this may be familiar to some who have seen my presentations at the AMR, but just to describe motivation for the relevance and goals of this work. the TCO modeling framework for the design and manufacturing of fuel cells in stationary markets is really intended to provide an expanded framework beyond just the direct manufacturing costs and prices of fuel cells to include other factors, which are, they could include life cycle analysis benefits and possible ancillary financial benefits, including carbon credits, so offset carbon emissions, health and environmental externalities, so less NOx and SOx, leading to less overall small particulates, which are very damaging to the respiratory system, particularly in the young and very old. One can look at end-of-life recycling, recovery of platinum, for example, in PEM, and reduce cost of building operations. So that's really the background, is to try to expand that framework and build a total cost assessment, including both private costs to the customer, but also societal benefits. Also identifying system designs that meet lowest manufacturing costs, and also we're looking at sensitivity to key cost assumptions such as energy costs or costs of materials and so forth. So some of the well-known barriers to fuel cell systems in general include high capital and installation costs, reliability, lifetime questions, and also the fact that potential policies and incentive programs may not fully value fuel cell total benefits. And it's kind of a general statement that could be applicable to other forms of cleaner renewable energy as well. So while I'm on this slide, I'll just say what this talk or this work is not. It's not a policy or a policy optimization analysis. It's not a market study, and it's not a business case analysis. So it's really more looking at manufacturing costs and societal benefits. Okay, just maybe a couple more background here. Fuel cell types considered are PEM and SOFC. And I'll note that we have pretty detailed LBL reports on both of these technologies. And the application space is, we're not covering forklifts here, but we're focused primarily on combined heat and power applications across 1 to 250 kilowatt sizes across a wide range of production volumes from 100 to 50,000. Those should be commas there, not periods. And then for backup power, it's spanning 1 to 50 kilowatts. Most of the backup power systems, or the largest deployment, is in the range of 2 to 5 kilowatts, so that's what we'll be focusing on. Just for background, in case people aren't familiar with combined heat and power, I think most people are. It's basically a distributed generation system which is providing both electricity and heat to a facility or to a building. That could be a turbine, it could be a fuel cell. There are many different types. And backup power applications can also come in a wide range of applications. Typically, you could see things, backup power deployed, perhaps where a diesel generator is deployed, and you could, or batteries in some cases, and that could be in radio cell phone towers. It could be in mobile units for lighting at sporting events, different applications for backup power. And then the DOE cost targets are shown there for reference for a 10 kilowatt CHP system and a 100 to 250 kilowatt system. And focusing on 2020, those equipment costs are targets are coming down to $1,000 per kilowatt. Okay, so the overall approach is a TCO model structure. First of all, we're making assumptions for the application and the size of the application. Here is primarily commercial buildings, so for example, a hospital and a CHP unit, which could be, say, 10 kilowatts or 50 kilowatts. Cost and price based on manufacturing volume per year assumption, and the location. So where is this being operated? Is it being operated in the Midwest or in California, etc.? And then those are inputs, and then the heart of the total cost model has three components. First, a manufacturing cost model, and so this is typically what you see past work from SA and from Battelle, direct manufacturing costs. Indirect manufacturing costs just refer to things like factory costs and overhead costs. The second piece here is a life cycle cost model. So this is a cost to a customer, which would include capital and installation, operations and maintenance. And for a fuel cell system, it also includes equipment replacement costs, like a stack replacement cost or a component cost, a compressor component replacement. The third piece here, which is more unique, I think, is what we call a life cycle impact assessment model. So this is monetizing health and greenhouse gas effects. So while the first two were private costs, this is more of a public or societal cost or benefit. And the key outputs, and I'll be describing that in more detail, and the key outputs include things like system manufacturing costs, so direct manufacturing costs, and then costs with corporate markups or factory gate prices. And then total cost metrics, these can include things like levelized cost of electricity, including total cost credits and total cost per year. Okay, so I'll just describe each of these boxes briefly. So costing approach, again, we're looking at, this is a bottom-up DFMA type of analysis of direct manufacturing costs. So on the lower right is ingredients that would go into the machine rate, or the cost per hour of annualized cost of a tool on the floor. So you can think of that as a robot tool or assembly tool or a deposition tool, and it includes the capital cost, financing cost of the tool, the operating energy cost, so that could be typically electricity at some commercial or industrial rate, and maintenance costs and floor space costs. So those are ingredients that go into the annualized cost of the tool, to which we add labor costs, material costs, consumables, scrap yield losses, and those are subject to a set of global assumptions for all modules for which we're doing costing, which include the discount rate, the inflation rate or rates, including the energy inflation rate for electricity, tool lifetimes. Typically we're assuming between 10 and 15 years for the tools. And then other costs are more corporate level costs, like R&D costs. G&A is general and administration, sales and marketing, product warranty costs, and those can get rolled up into a corporate markup. So we have more details for the assumptions and the backup, and if people are interested, we can discuss that more. But in general, I would say that we are assuming a high degree of automation and faster throughput, and an evolving an evolution to higher yields, which is assuming better defect metrology and inspection and feedback processes. So in the upper right is just showing a fairly automated assembly line from Altergy Systems and Folsom, their maker of backup power systems, as an example. Okay, the second component here is the life cycle cost model, or use phase modeling. So this is the calculation of total costs for a owner, say it's a building owner or a owner of the fuel cell system, in, say, a commercial building like a hospital or a dormitory, or maybe it's a campus. And so basically what we have on the bottom are load profiles for electrical demand, electricity and cooling demand, and on the lower right, heating demand profiles, shown here as daily hot water, but we also have space heating demand across weekday and weekend days for a number of buildings. So there's 16 commercial building types across several geographies, across the U.S. basically, across the, I forget how many climate zones, but the many climate zones of the U.S. So that's an example of an input that we're taking, and then from that, depending on the size of the fuel cell system, we calculate the load shape or the duty cycle of the fuel cell providing electricity to the facility, as well as the fuel provision, or the heat that's provided by the fuel cell system. And then we also calculate any purchased electricity or purchased additional fuel that is needed at the site. And this also includes things like the demand charges to the utility, which is a charge for the peak demand, the peak monthly demand. So if the fuel cell is successful, you can really offset that peak monthly demand and get savings. So the output of this is the overall annual cost of operation as well as avoided emissions. The third piece of this is our LCIA, or Life Cycle Impact Assessment for Environmental and Health Externalities. And I'll be discussing this further later, but again, we start with defining a geography of interest. So we have 6 cities we're looking at, and we define a building type such as, say, a small hotel. And from this set of, these are profiles from prototypical commercial buildings from NREL that are then modeled in Energy Plus. So from the building load shapes, we can derive the fuel cell load shapes for electricity and heating. And from that, we can calculate the displaced, if any, displaced heating fuels and displaced grid power, and then calculate a net change in pollutant emissions, which could be a net change in CO2 emissions or a net change in NOx and SOx. And that is an input into a health impact model. And we're using a model which is called APEEP, which has been updated to AP2, and the important thing to note there is that has been the model that's been used by the National Academy of Sciences in the past. And that translates into monetized impact. Okay, again, I'll discuss this in greater detail in the third section of the talk. Okay, so now I'll discuss PEM and SFC fuel cell system direct manufacturing costs, and I'll just say that these are really some of the highlights, and I don't really go into great detail in these results, but there is a lot more detail contained in the LBL reports, and I'll show some links for those at the end of the talk. So for our CHP systems, we start with the system diagram, and we start with the stack. So this is where we do a lot of the detailed bottom-up DFMA costing for the fuel cell stack. And then we build out, or we kind of enumerate and develop individual subsystems for the system schematic, and also to develop component requirements for the balance of plant or the balance of system that is the non-fuel cell component costs. So we have a reformer, air supply, water makeup, coolant, which these are cooled. We're assuming that the fuel cell stack is cooled, and there's a thermal host, and this could be for the PEM something like water heating or some space heating, some applications. There's a power conditioning subsystem, and this is typically for this application, it's a DC to AC inverter, and then there are controls and meters, and there can be a ventilation air supply. So each of these is kind of sized, and we build out a bill of materials for the balance of plant costing. So again, the stack is primarily bottom up, and the other components are primarily purchased. And so the output heat temperature in this case is relatively low, but it's 65 C. Okay. And then in terms of the manufacturing approaches, I just have a table here of stack components for a PEM stack from the membrane, catalyst-coated membrane, GDL, and bipolar plates and down. The stars indicate these are units over which are components over for which we've done full DFMA costing. We assume that we're purchasing Nafion, and then for others we're doing bottom-up costing. For the CCM, we're assuming a dual decal with slot die coating. And the references for the manufacturing approaches, the equipment costs, material costs, are from patent reviews, industry inputs, literature reviews, and again, for PEM, we were working fairly closely with Ballard in Vancouver. For the functional specs, so these are kind of the operating parameters, excuse me, that are assumed for the CHP system. We have a platinum loading of about 0.5 milligram per centimeter squared. So it's a higher platinum loading than you would see in automotive. We have a list of parameters that I won't go over in detail, but just say that the average, excuse me, net electrical efficiency is 32% for PEM. The total efficiency is in the low 80s, and the stack current density is 0.56 amps per centimeter squared. So this slide has a typo, so I don't show the metal plate cost model, but I am showing the CCM. So the CCM really is a critical component for PEM. And I'm showing a schematic of a slot die coating process. So there's an ink tank with the cathode ink, and then there's a pump. There's a roll-to-roll process with a membrane and backing layer which is assumed, which is fed through a drying oven, and then we have some optical and X-ray scanning defect metrology assumed. And this is showing that there is a high cost for lower production volume. The natural unit is meters squared, above 1,000 meters per squared, but dropping over time. With manufacturing production volume. And on the right is showing the percentage cost breakdown as a function of increasing volume, going from 1 kilowatt, 100 systems per year, to 50,000 systems per year, out to 100 kilowatts for the same increase in systems per year. So at lower volume, the capital costs are dominating the costs, and as you go to higher volume, the direct materials are dominating. And overall, the labor costs are quite small. An overall roll-up, so we do something similar for all of the other components that are shown in this table on the left, the CCM, the GDL, and the bipolar plates. So an overall system, this is the direct manufacturing cost system roll-up for the CHP PEM case, is shown on the left, as again for a 10 kilowatt system and a 100 kilowatt system as a function of production volume. And so what you're seeing is that the balance of plant, which is shown above here, is, at 2/3 or more of the overall cost in general, and that for the stack cost, these plots on the right are showing the percentage breakdown of stack costs. The CCM is the dominant component, that's the dark blue, and the other important cost components are the GDL and the plates. The BPP are the bipolar plates. And platinum here, we're assuming an average platinum cost per ounce over the last 10 years because platinum cost has been quite variable, and the average over the last 10 years is about $1,400 per ounce. And platinum does make up a good chunk of the CCM cost. In terms of balance of plant, we've seen that the power subsystem and the inverter in particular is a large piece of the balance of plant costs, followed by fuel processor, and miscellaneous. Miscellaneous are things like the enclosure and labor. This is just showing, again, a breakdown of the balance of plant costs as a pie chart for 100 systems per year to 10,000 systems per year. And in general, under the assumptions we're making here, we see a lot more cost reduction with scaling for the stack than with the balance of plant components. There's some reduction in the balance of plant, but not as great. Just a sensitivity plot here showing that process yield and power density are important cost sensitivities at all the volumes, and that the stack material cost on the right here becomes more sensitive at high production volumes, and the stack capital costs are more sensitive at lower production volumes. Okay, I'll just pivot now to the SOFC CHP system, and our base unit there was 50 kilowatt system. Again, similar methodology in starting out from from the fuel cell stack as subsystem A. There is a smaller reformer unit. We're assuming partial reforming, internal reforming, so there's a smaller unit for external reforming. The temperatures that we're assuming here are between 700 and 800 degrees C of the stack operation, assuming anode supported cell. And it's also showing some heat exchange to preheat the reactant air from the burner exhaust, bringing up the air temperature closer to 600 C. There's also some internal heat exchange in the stack. And again, the thermal host, the temperature can be higher, a lot higher than in the PEM case. So for system designs and functional specs, similar methodology of building out component through bottom-up analysis. So I have here for the first 5 or 6 are the electrode, electrolyte cell for the anode, interlayer electrolyte, interlayer and cathode. And again, this is an anode-supported cell utilizing YSC, nickel, and LSM. And we're relying on tape casting of the thicker anode and then screen printing for the other EEA layers. And this is an LSM for the cathode, and then stamped metal plates with stainless steel 441 for the plates, and down the line there. Functional specs here for the SOFC case. Again, I'll just note that the system net electrical efficiency at the higher temperature is much higher, approaching 60%, and the total efficiency is similar in the low 80s, and the current density is approximately 0.35 amps per centimeter squared for comparison. Okay, just a few modules again for the SOFC case. So this is the EEA process, kind of tape casting, schematic flow of a thick layer. The EEA cost plot, these are for a 100 kilowatt system, are about $200 and going down to below $100 per kilowatt at higher volume, and it's again dominated by material cost at higher volume. For the metal plates, we're assuming a process which looks something like this: a stamper followed by a cleaning and drying module. There's a deposition of a coating layer, manganese cobalt oxide spinel, and then an inspection. And again, here we're seeing the plates are coming in below 50 per kilowatt, 100 systems per year, and dropping below $20 per kilowatt at higher volume. Okay, so system costs for the 10 and 100 kilowatt CHP. The stack cost is dominated by the EEA, shown on the right, and the balance of plant again are, roughly 2/3 or more of the overall cost. So a similar kind of fraction as before. And for the 100 kilowatt system, the direct cost is below $600 per kilowatt at high volume. This is quite high volume, of course, 100 kilowatt times 50,000 units per year. For the balance of plant, the SOFC has, as a higher temperature system, has a simpler, fewer components in the balance of plant, and the power system is dominant. The fuel processing is a lower fraction and is a smaller unit. So some CHP system equipment cost estimates in this work, which are bolded, versus DOE targets for 2020. And these DOE targets, the units correspond to the annual production volume stated by the DOE. So the PEM with a nominal 50% corporate markup is exceeding the DOE 2020 targets in this work, but the SOFC is close, exceeding or meeting those DOE targets, again at these pretty high volumes, 10 kilowatt, 50,000 units per year, or 100. So this would be a 100 megawatt system for the bottom row. Okay, finally I just have two more slides on this section, which is for backup power. Backup power system schematic is simpler. There's an H2 storage. This could be a K-ball or cylinder. Dry H2, there's no humidification here. And instead of AC to DC inverter, there's typically a DC converter, auxiliary battery, blower for the air. There's no active cooling, and so it's a simpler system overall. Functional specs here. So in this case, we're assuming a lower platinum loading of 0.3 milligrams per centimeter squared. Before, for the CHP, it was 0.5. And we're also assuming metal plates with the lower lifetime of the backup power system. So the current density is lower. It had been 0.56 for the PEM, so it's about 30% lower at 0.41. And the system direct manufacturing costs, so again, I'm looking at 5 kilowatt. That's the most common size. The direct costs are shown here, approaching below 5,000 per kilowatt at low volume, and dropping to below 2,000 per kilowatt direct cost at about 1,000 units per year. Okay, I'll just spend a few slides on cost comparisons to market data and other models. So the first thing I wanted to just mention is that there is a lot of data for the Japanese micro CHP product, NFARM. So these are small units, so this is kind of at the extreme end of what we've modeled. We really haven't gone below 1 kilowatt, but we can think of 1 kilowatt as being close. So not only 0.7 kilowatt to 1 kilowatt system sizes. But what you see is, and I would say that there is, a strong incentive in Japan. There's strong incentives which have been dropping over time for the market adoption of these units. But what we have seen is a 50% cost reduction from 2009 to 2014. And so it's interesting to try to understand what's driving that, and that corresponds to a learning rate of about 17%. A learning rate is related to the cost reduction for every doubling in cumulative volume. So on the right, I've shown the LBL direct cost model for 1 kilowatt, and I've shown the stack, the balance of plant components, and I've shown a markup of 50% to 100% in the last two shaded regions. Just put a point there for the 2014 price per kilowatt, which is about 22,000. So we don't know exactly what the markups are, so this is kind of approximate, but we do know that the balance of plant is, there are a lot of components in that system with water heating and storage tank. And so what this can help understand is the economy of scale. So what we do know is that in 2009, for a given vendor, there are about 1,000 units per year, and now it's up to about 20,000 units. So from that approximate estimate of 1,300 units per year to 20,000 per unit a year, we are seeing about a 23% cost reduction from just economies of scale. So this does not include things like platinum reduction or balance of plant integration. We're also estimating a similar cost reduction of about 19% from publicly announced design and performance improvements. So that is from lower platinum loading and from balance of plant integration. And that leaves about a 20% residual, which is attributed to other factors. And that could be things like, it could be the margin is changing. It could also be because as the industry is scaling up, we're seeing more suppliers and there's more cost reduction from supply competition. All right, so this is now a cost modeling comparison for the stack direct manufacturing cost for this work compared to some earlier work. So this is maybe a little bit older, but the Manhattan Project, DoD project from 2011, and strategic analysis from 2012 for matched system size and production volume, similar platinum loading, and looking at the stack direct manufacturing cost versus yield. For the Manhattan Project, it was about $850, but at low yield, and we're getting something similar actually. But at higher yield in the manufacturing process, it was about $480, and we're getting at much higher yield about $450. So it's ballpark very similar. Strategic analysis was lower, but with a lower platinum loading. Okay, one more PEM comparison. This is looking again, this is what I showed before, a 5 kilowatt backup system, direct cost plot, but now I've added just some markups, so a 25% markup with the 50% markup and with the 75% markup. There was a study from NREL a couple of years ago for backup power systems and expenditures or costs, and so for kind of the base backup power system, it was about 30,000 to the system, so it's about 5,700 per kilowatt. That's this line here. And we're assuming that the production volume a few years ago was pretty low in the hundreds of units, so that's kind of the regime. We're in the low volume regime. And it roughly corresponds to a 50% markup. Again, this is kind of approximate. We don't know exactly how these markups look. It could change over time. But it's just showing that if this is where we are approximately, then increasing production volumes to above 1,000 units per year can achieve significant cost reductions. That's about a 50% cost reduction from 6,000 to 3,000 and below. Okay, finally, I just want to share some total system cost data from California's Self-Generation Incentive Program. So publicly available data in their database. This is just an incentive program which would add to the federal incentives for installing a fuel cell or other clean, renewable distributed generation in California. So the incentive for fuel cells had been, at around 2,000 per kilowatt, and they've been dropping over time by about 10% per year. Now they're at approximately 1,500 per kilowatt. So what I'm showing here, and I just focus on the left, is SOFC installed price over time. These are the eligible costs, so the post-incentive prices will be much lower. But you're not really seeing a cost reduction. If anything, it's kind of edging upward. And the estimated annual volume in going from here to here is, hundreds of units per year. And this represents about a 6 to 7 doublings. So if you're assuming a 10% learning rate, it should correspond to 50% cost reduction. If you're assuming a higher learning rate, 15%, you'd expect maybe a 66 to 70% cost reduction. So we're not seeing that. So it's difficult to estimate the manufacturing costs without further information. There's possibly much higher costs, underlying manufacturing costs than the cost model here or in other cost models. And this could be coming, if that's the case, it could be coming from a lower degree of automation or lower process yield, potentially higher material costs or underestimated materials or costs, more hands-on engineering labor costs. Okay, so the last part of my talk, I'd like to discuss externality evaluation and give an example of that. So again, this is the slide that I showed before. So the bottom line here is to come up with a net change in pollutant emission profile, and then to provide a monetized impact using existing health impact models such as APEEP. So this is just a slightly deeper dive into that, where we are starting with geographies. We have 6 different cities: San Diego, Phoenix, Chicago, Houston, and New York. And then we assume our fuel cell costs and application parameters. Again, this could be, say, a small hospital or medium-sized healthcare facility in New York, say, and that corresponds to the load shapes and the fuel cell load shapes and the fuel cell cost. So that's the fuel cell scenario. And that's compared to a baseline scenario or a reference scenario, which is basically a case with no fuel cell. And so we calculate the net emissions. So these are avoided emissions from power plants. So these are generally modeled at the stack level, so at some height, smokestack level. And then at the ground level, the net emissions change for building heating, and then any additional emissions from the fuel cell system itself. And so these translate into a change in tons per kilowatt hour in emissions from each kilowatt hour from the fuel cell. So this is like a change in kilograms of SOx for every kilowatt hour of the fuel cell. And on the other side of this is the APEEP model, which is giving us a dollars per ton monetized damage as a function of region in the country. And this is utilizing several steps, starting from the pollution emissions modification, so the reduction in SO2, say, to the air quality modeling, and then the intake fraction to the human population, again, and then the dose response and the monetized damage. And these damages are based on methodology of value of a statistical life at about 6 million. So these two factors are then multiplied, so the change in tons of pollutant per kilowatt hour from the fuel cell times the dollar per ton for each ton of pollutant, and that gives you a dollar per kilowatt hour benefit. So the dollar per kilowatt hour benefit is plotted here for an example of a 50 kilowatt small hotel CHP using the LTPEM system. And what you're seeing is that for the health and environmental savings, and just focus on the green bar, which is our latest, most updated estimate for externality benefits. It's very sizable in Minneapolis and Chicago, so in the upper Midwest. The greenhouse gas benefits, so the benefit of greenhouse gas or CO2 savings is much lower. So these are around 10 cents per kilowatt hour. These are below 2 cents per kilowatt hour. But overall, if you sum them, you're getting about 10, 11 cents in Chicago and close to that in Minneapolis. And so really those should be understood as the sub-region benefit. So it's hard to say that that's, at the city level, we don't quite have that resolution, but it's more result at the EGRID sub-region level. And what's driving that is really the fact that you're offsetting dirtier or higher carbon intensity electricity in these regions of the United States. So this is showing the emissions factor for different EGRID regions. So there are 22 regions, and so MROW, where Minnesota is one of the higher ones, as is RCW, which is here, also one of the higher ones right here. So earlier we'd used marginal emission factors by NERC region, but we've transitioned to higher result EGRID subregions. And the thing to note is that this emissions factor can vary by more than a factor of 2 between regions, between the dirtiest regions to the cleanest regions, California, for example. Okay, so if we put all of this together, we come up with a levelized cost of electricity, and this metric, which I'm calling a levelized cost of electricity with TCO credits. So again, similar example, 50 kilowatt low temperature PEM CHP in a hotel at about 2,900 kilowatts per kilowatt install cost. And the first bar here is the purchased electricity cost, so it's the average commercial rate of electricity by city here. So that's without a fuel cell. And the second, third, fourth, the other bars are all with fuel cell power. And so this first step down is, so the second bar is the cost of electricity, the levelized cost of electricity with fuel cells. The first step down is adding the benefit of fuel savings at this site. And then the second big step down is adding the greenhouse gas and human health and environmental savings. So that's adding this benefit that I showed above here for each of these cities. And so you get a big benefit in Minneapolis and Chicago and smaller benefits in other regions. Okay, so that's kind of a snapshot, however, of where we are in 2015, say. Okay, but the question is, how does this vary over time? Because as you all know, the EPA has a Clean Power Plan to 2030, which will provide a cleaner grid and will reduce the benefits of fuel cell CHP because each kilowatt hour of offset electricity will be cleaner and have lower greenhouse gas emissions and lower NOx and SOx. As an example of that, it's just showing the NOx average reduction out to 2025 is about 50% on average, and the SOx reduction is 80% on average out to 2025. Similarly, one can look at the average reduction and actually the resolved reduction in CO2, the tons per kilowatt hour from the grid for SOx and NOx out to 2030. So that's what this is showing. And on average, there's a 13% reduction in CO2, 80% reduction in SOx, 50% reduction in NOx. And those are out to 2025, so I just hold those constant out to 2030. So finally, what this is showing is a cash flow analysis. So just focusing on the lower right, this is a cash flow for fuel cell system. Similar system, same region, 50 kilowatt PEM, small hotel in Chicago, but now looking across this 15-year time span, 2016 to 2030. And you can think of this as like cash flow for your solar PV system where you're incurring an upfront cost for the PV, but your PV is saving you money, it's saving you fuel costs. So this is the blue line is the fuel cell total cost of ownership savings. So this is the savings that you're getting on a societal basis from the fuel cell system, which is fixed. So this is assuming a fixed and static grid. And so you get a cash positive investment as shown here. But now one can ask the question, what happens under the assumptions for this region in Chicago for a cleaner grid and a lower criterion emission pollutants. And so what you see here, again, focusing on the lower right, is that the total cost of ownership savings are dropping over time, getting much lower, and this is because the grid is getting cleaner and the criterion pollutants are getting smaller. So every kilowatt hour of fuel cell energy has less benefit. So this curve, the cash flow curve, is starting to bend down, but it's still positive, so you're still getting a positive investment. And in a sense, I've used the average emission factors change here, so this is kind of like a bounding case. All right. So just to conclude my talk now, we have seen that at very high volume, stack and system costs for PM are getting down to $220 and $900 per kilowatt. And it's about 25% to 30% lower for SOC at high volume. And that for CHP systems for both PEM and SOC, the balance of plant costs are a higher fraction overall than the stack cost for the manufacturing assumptions here. And again, this is assuming a lot of cost reductions and scaling, automation, and improved yields for the stack and lower balance of plant cost reduction with volume. We've looked at a few case studies of modeled prices versus market prices compared to Japan, micro CHP, backup power. The SOC case is harder to compare. There's, the data isn't really showing a cost reduction, at least from California. And then by including externalities, fuel cell CHP has economic applicability in a subset of commercial buildings. So we've seen some buildings are more favorable than others, and that has to do with like the heating and electricity demand. And the regions also which most benefit are regions of the country with high carbon intensity electricity from the grid, as we've seen, the upper Midwest, as an example. And so this spatial dependency of externality benefits suggests that regional incentives tied to the regional grid electricity, carbon intensity, and heating fuel types may be appropriate. So I just want to refer again to two fairly detailed LDL reports, the first on the low temperature PEM technology. So this is a 2014 report. We will have an updated report posted soon. And there's also an SOC report, which is available at the DOE site. This was just released earlier this year. I'd like to thank the funding support from the FCTO office and thank Donna and Jason and Sunita. And also thanks to many of the folks here. I want to thank in particular Professor Massimo Santarelli for collaborating on this work and his visiting students, some of his visiting students. And I also want to note that this list is kind of a partial list. This is, I think I copied this primarily for the SOC work. So there's a similar list which applies to the PEM work as well. Okay, so again, the Q&A here, as Chris mentioned, and finally I want to just thank everyone for your attention.
Great, thank you, Max. I'm pulling up the questions here on the screen. The first one goes back to the beginning of your talk around slide 6. They just wanted to know what the cost target volume assumption was and the whether or not the cost targets are for equipment only, and I can answer that. It is for equipment only.
Those are for equipment, and the assumptions, I believe, was informed by other cost modeling work, and again, the assumptions are corresponding not to a specific technology. So this is kind of, it's not saying this is for SOFC technology or PEM technology, but fuel cell CHP. And the targets are also corresponding to a annual production volume. So I mentioned, if I can find it, well, anyways, there's a slide later, which is showing the production volume. So these targets are corresponding to 500 megawatts at low power and about 100 megawatts at high power. So that's what I could say.
Okay, great. The next question was more general. It says PEMFC and SOFC, with the possible exception of Bloom, are the more recent entrants into the commercial CHP market relative to the molten carbonate and phos acid. Why did you choose to only model the solid oxide and PEM rather than all the commercially available technologies? And that's probably more programmatic. The Fuel Cell Technologies Office is within energy efficiency, renewable energy. The Fossil Energy Office at DOE focuses on these higher temperature, larger power generating fuel cell systems.
Right. I would say that I think there was desire to look at exactly that, emerging technology applications, and so there has been less in this space, kind of the lower power space for PEM and for SOFC, and those are market entrants now. There's some interest in CHP in the 1 and 2 kilowatt system sizes in Europe, for example, solid power, and other applications in Japan, or I should say SOFC, CHP in Japan as well.
Okay. Let's see, a few more. On the manufacturing costs, is it not redundant to include salvage price and then also a separate depreciation factor?
Yeah, I mean, I think we weren't seeing a big salvage value, so I think that one, I mean, some of these components are not, are not so big. I mean, for this one, it's really the capital is dominant, the energy cost is second, and the building floor space is a smaller factor. So these others are smaller factors.
Okay. And then here's more of a comment rather than a question. Let's see. You seem to ignore savings that result from not having to enhance grid capacity. In places like Tokyo and similar urban settings, it's very expensive to expand the transmission and distribution. The person who asked the question mentioned that they learned in some cases the cost of fuel cell CHP is less than the cost for the utility to expand the capacity to deliver the amount of power the fuel cell system supplies. They just said you might want to consider this.
Yeah, that's a good point. I think if I understand that, I think it's a general point for looking at the various value propositions of distributed generation and reducing potentially the need for utility grid or electricity grid infrastructure, which could include transmission and distribution. So Japan, I mean, this example, I won't skip to that slide, but Japan does have a much higher cost of electricity, so the value or the benefit of the financial benefit of fuel cells is, it's going to be easier to realize there. But it's a good point. We haven't explicitly included the value. I mean, it's hard to put that into a number of the value or the benefit of reduced grid congestion or reduced grid infrastructure or potentially providing something for grid flexibility in some cases. So it's a good point.
Okay, we have time for a few more questions, and they keep popping up. Let's see. How do we get private sector to purchase fuel cells when they look at cost to their pocketbook and not total societal cost? That's kind of a...
Right. I mean, that's kind of the, again, I would say that's that's a question, a good question for fuel cells, but it's a wider question. It's like, how do you incent a cleaner form of, if electric vehicles make sense in places where there's a cleaner grid, how do you incent that if the cost is, 10,000 more, and the societal benefit is defraying that. And so I don't have a pithy answer to that, except to say that what we're trying to do here is to try to show the quantification, or at least the range of potential benefits. So the range would vary on, what your price of carbon is, for example, and to say that, these are dependent on where you build it, and you would get more benefit. And it's not just this study which is suggesting that, but other studies looking at wind and solar have shown that the value of wind from a societal basis is, the benefit is higher in a place like Ohio. That you can try to develop policies or programs or incentives that can try to factor that in. I mean, the carbon price is one thing, clearly, but can you factor in something which is a credit, a societal credit? But again, the purpose of this work was not to do policy analysis or policy development. I mean, how you would implement that, fairly or equitably or reasonably is kind of a whole different question. So I don't have a short answer.
Oh, okay. We'll move on to another question. It says, any farm reports seem to suggest that a higher CO2 reduction from using fuel cells for CHP. Why are the reductions here lower? Is it grid differences or differences in heat and electricity usage? Any farm suggests that the overall efficiencies of 90%, is this potentially a reason?
Yeah, so I assume what the question, again, I'm not sure I can find the slide instantly, but let me just try to find it. So I assume, let's see, I'm not sure where the slide that I think it's blocked by the, anyways, I assume here it is, I think. Assume what the question is saying is that I mentioned that between the greenhouse gas benefits and the health and environmental savings, I commented that at least for the societal cost of carbon of about $40 per ton, the greenhouse gas benefits are much lower than the health and environmental benefits, at least in regions of high grid, high carbon intensive electricity. And I think the question is, in Japan, that seems to be different, that these benefits are much higher. Is that your read of the question, Donna?
Yeah, that's right.
So yeah, that could be related to the grid intensity in Japan. I'm not that familiar with the grid in Japan. I do know that since the Fukushima earthquake and the tsunami, a lot of the nuclear plants went down, and those are zero carbon. And so there is an increase in fossil production, both coal and natural gas, in the electricity grid. So there's definitely a change in the emissions factor, or the CO2 emissions factor in Japan, which could improve the greenhouse gas benefits for fuel cells. But the absolute, I don't have that at my fingertips.
Okay, great. Well, I think we're running out of time, and these slides will be available afterwards, and also you could contact us with the remaining questions. I'll hand it back over to Chris.
Thank you, Donna. Max, if you want to go to the very last slide there, the contact information.
Yes. Okay.
I guess I'd just like to thank you, Max and Donna, for a very informative presentation and Q&A section there at the end. It's going to conclude our webinar today for our audience. If we didn't get to your questions, please feel free to email the presenter directly, and we'll try and get you a response in a timely manner. Again, I'd like to thank everyone for joining in. To remind you that the webinar and slides will be available online at the Fuel Cell Webinars website shown in about 10 days. Also, I encourage everyone to sign up for our monthly newsletter, which includes information and registration for upcoming webinars. You can sign up for that at the website shown as well. Have a great rest of your week, everyone. Bye-bye.
Thank you, everyone. Thanks, Chris and Donna. I guess I'll be logging off.